Okay, welcome everyone back to the second part of the eighth lecture. So basically I want to show you some classification results regarding fusion categories. Of course, I'm going to explain what fusion categories are, but basically there's semi-simple versions of these tensor and Fiat categories we've seen in the previous lecture and the previous lectures actually, like the targets for quantum invariance. And if you remember, well, or if you have seen the first part of this lecture, then you might remember that we had those numerical invariants we wanted to assign to, or we assigned actually to those categories, Perron Frobenius dimensions and fusion graphs and so on. And I will show you zillions of examples in this lecture. So if last time was a bit fast for you, don't worry, we'll see zillions of examples. Um, yeah, so let's just jump right into it. Before I can show you examples, I need to basically tell you what I'm going to classify. And it's pretty simple. And again, there will be some weekly, multi, we have seen this in the last lecture. It depends a bit on your on your um, on your category itself, whether it's rigid or pivotal. There's lots of adjectives. But the main point is I want it to be fusion. That's the name. It comes from fusion category. It comes from physics, fusion categories. And basically this means it's a semi-simple Fiat category. So semi-simple. The crucial word is semi-simple. Crucial. Okay. And it's semi-simple and has all the structures you would think of some diagram category should have, like pivotal, it's monoidal, and it's also a part of linear algebra, so it's K-linear and so on. And the right equivalence for them is, of course, linear, additive, and monoidal. And the point is, for those guys, I don't really have to care whether I define them as uh, a semi-simple Fiat categories or a semi-simple tensor categories, because they are semi-simple, and in this case, those two notions agree. And it's just because semi-simple is a stronger notion than the beginning. The standard examples you should keep in mind are basically finite dimensional modules over semi-simple Hopf algebra. Or, as we've seen in the previous lecture, basically a finite group, you take finite dimensional modules, and you kind of want it to be semi-simple. So you need that the order of the group does not divide the characteristic of the field. Right? This was this P does not divide M condition. But then you are basically good to go. This is a good source of examples. There are also graded vector spaces, of course, because graded vector spaces are just very, very easy. There are quite a few examples of those fusion categories. The point is they are semi-simple. And for semi-simple categories, remember that basically home spaces, so here's one simple module, here's another simple module, and home spaces between them are trivial. Right? So home between two simple modules in a semi-simple category is either 1 or 0, depending whether L is isomorphic to L prime or not. Well, L not isomorphic to L prime. So home spaces are very, very easy in semi-simple categories. In some sense, this should tell you that any invariant, such as Perron Frobenius dimensions, which we've seen last time, is only concerned about most objects. It should be pretty bad for non-semi-simple categories. It's not really bad, it's okay, but it's also not really strong. But it should be extremely good for semi-simple categories, because basically semi-simple categories only have trivial home spaces anyway. And that's true. In a certain sense, that's true. Numerical invariants are pretty good for those fusion categories, for those semi-simple categories. Here's a certain proposition. It's not super exciting. It just makes life a little bit easier. For example, the regular object, or a regular object to be completely precise, is just given by taking the sum of the Frobenius dimensions of the simple objects. Not very exciting. Well, it's okay to read, right? So something like left and right, let's go inside. The fusion coefficients are circling and so on. Not not super important. So something to just read if you read the lecture notes, which are of course linked in the description below. The proof, the only thing the proof basically uses is versions of Schur's lemma, and Schur's lemma was this one. I just showed you. This was Schur's lemma. Sure. Home spaces are trivial, and you use it in several well incarnations. But that's basically the proof of this whole proposition. So the home spaces are trivial really helps. Um, so let me discuss an example. And the example is as follows. We take a finite group, and remember we want this condition for semi-simplicity, so don't want the characteristic to divide the order. The easiest thing you could start with, oh, let's just ignore that completely and just start with the complex numbers. Everything is nice with the complex numbers, and we're happy. And for any subgroup H, you can take the direct sum over the objects in the corresponding graded category. Right? Remember here in the graded categories, the objects are just G prime, so just the group elements and so on. So you can definitely just take all the H's in your subgroup, and you get an algebra object in vect. And it turns out that the modules over this algebra object are exactly isomorphic to the corresponding finite dimensional modules over your subgroup. And you can beef this up a little bit, and what you would get is another source of examples of fusion categories. So you can throw in some of those funny co-cycles, sorry, co-chains, to twist the multiplication, and you get what is called group-like fusion categories. These are really just basically of the form finite dimensional modules of some group, but now your multiplication is twisted by some numbers. And this cosine is just a those co-chains, remember, it's just let's say a smart way to encode where to put certain scalars. So everything is the same as before, but twisted by scalars. And this is another source of examples of those fusion categories. Funnily, so that's kind of the takeaway message. So those examples were group graded things, finite dimensional modules of a group. Here is another source of examples, finite dimensional modules of a group but twisted. So you might ask, maybe all fusion categories are of that form? That would be bad. Why would that be bad? Basically because there is no topology in those fusion categories. The braiding is very boring. Luckily, there's another source, there's another class of fusion categories, and the outcome of this lectures, of this discussion of this lecture, I won't be able to prove everything. So it's also not strictly, well, it's not proven in the lecture notes as well, because it gets a bit involved. But basically, the outcome of this lecture is that fusion categories, up to some exotic exceptions, are basically given by three types. It's vector G, up to some twisting that you can do. It's rep G or mod G, whatever I called it, mod G. So finite dimensional modules, maybe FD mod G. And it's those things you call Valinde categories. And they will come here. And these are really good for defining quantum invariance. Anyway, so because now we jump into Valinde categories, let me summarize what I just said here. So basically, this was just getting the notation set up. We're now caring about the easiest possible example, which is not trivial in our setup, and this is the semi-simple case. And in this case, terminology from physics, in the end, is these things are called fusion categories. And the main examples I wrote down up to this point is everything related to finite groups, basically. And that's boring from the viewpoint of quantum topology. So let's try to write down another example of those categories. And it turns out that this is not easy. Yeah? It's not so easy to define those well-limited categories. And I will a little bit be hand-wavy, and it will take me basically the rest of the other two lectures to really define it, at least in a certain case. And I will do it completely diagrammatically. For this lecture, just go with it and we will basically just assume that those things exist. And that's exactly what I just said is exactly what I write here. So there's this important family. These are the well-limited categories. These are really extremely important for constructing quantum invariants. Basically all quantum invariants that are non-trivial in one way or the other will come down to well-limited categories. However, they are really not all that easy to construct. And I will postpone this construction to later sections. Okay, so I will give a diagrammatic construction for certain parts of it, and maybe later a diagrammatic construction for others. But the main theorem, which is not so easy to prove, as I said, is for any finite dimensional, whatever, semi-simple complex Lie algebra, and any choice of basically level k, there exists such a fusion category, which is a C-linear category, and it's denoted by FD mod KQG. These are just valid categories. So that's just, all this is saying is that there's a huge family of these things. So first you can choose a Lie algebra. And if you don't know what that means, you basically can choose, let's say, SL, an SL thing, you can choose an SO thing, you can choose an SP thing. Let's say let's say what you can do. An SL, SLN, an SON, or an SP2N. SP is always equal. So there's already a whole family by just choosing the right Lie algebra. And for each Lie algebra, you can additionally choose a parameter. So this guy, which is usually called the level. So we get a huge parameter family of those things. And for all of those choices, there exists a well-limited category. Okay? And this is just very hard to prove, at least out of the blue, like from a vacuum, what I'm trying to do here. But I will give you a construction later. For now, just believe this theorem is true. There's a huge family of those fusion categories, semi-simple, which are not group-like, they are different. I haven't told you that they're not group-like, but they're different. We will see several examples in a few pages down. Basically, the rest of this lecture will be about examples of those fusion categories. Huge family of them. Each one of them, that's kind of the outcome, will give you a nice quantum environment. So let me, for the sake of concreteness, let me do a specific case. So let's just, the easiest Lie algebra, which is non-trivial, I can think of, just think of Lie algebras as being matrix algebras, and the easiest matrix algebra you could think of would be SM2, probably. And so you get those well-limited categories depending on k. For any k, you could for any level you could choose this well-limited category. So let's just fix some. Let's just fix some k greater or equal to 2. Doesn't matter so much. Then the category is a ribbon fusion category. So it's also ribbon. There's braiding and everything. And it has simple objects indexed by everything from 0 up to k minus 2. Okay. And the simple objects, well, the zeroth object is a trivial object, and all other simple objects are self-dual. So you have 0 up to k minus 2, the indexing set for simple objects. All of them are self-dual. And yeah, so you certainly have a growing number of simple objects. And the fusion rule for them is actually pretty easy. You can write down in a closed formula. Don't look at it too much. It's not so important. Well, it is super important, of course, but it's not so important to get it right away. The point is, it's a closed formula. It's just a very easy closed formula, and it's called the Clebsch-Gordon rule. Okay. Whatever. That's just what it's called. And let us discuss this for some small instances of k. So for each k, you have 0 up to k minus 2 simple objects, and they have a very, very easy fusion rule. And with very, very easy, I mean you can write down a closed formula. And that's really rare, right? Not often you can really write down a closed formula, but in this case, you could really write down a closed formula. And it's not so bad. It fits in one line. So it can't be that bad. But let's just discuss it for small k, just to get a feeling what those categories are. As I said, I postponed the construction to later. For now, just believe me that those things exist. Okay, so the smallest value for k, so k is bigger or equal to 2, would be 2. And in this case, well, there's not much to set. It's just vect, okay? And everything is over the complex number, so it's just vect c. And of course, vect c has just Perron-Frobenius dimension 1. Okay, and the corresponding generating object of vect c has Perron-Frobenius. So the fusion generator has Perron-Frobenius dimension, and then now it gets funny. It's 2 cosine. So as I said, it can be a real number. So here's the cosine, and it's pi over 2, which is of course just 1. So it's 90 degrees. It's a 90 degrees angle, right? Pi over 2. It's a 90 degrees angle. So it's just cosine pi over 2, and this 2 here is a level. That's what I want to say. This is k. And this would be kind of general. So that's why I want to write it like this. It looks a little bit silly that I write 1 as 2 times cosine pi over 2. Yeah. Okay, for k equals 3. So the point is L1 will always be the fusion generator. And this thing will always have Perron-Frobenius dimension cosine pi over pi over 3. Pi over k. So pi over k. And k for k equals 3 is in particular pi 2 cosine pi over 3. And this is how it looks like in this case. You have 2 simple objects, namely the identity, which is L0 and L1. And L1 has this fusion graph, this anti-diagonal fusion matrix, and the Perron-Frobenius dimension of this thing is easy to write down. It's 2 cosine pi over 3. In particular, the PF dimension of the whole beast is just, this by the way also 1. The dimension of the whole beast is just 1 squared plus 1 squared, which is 1, which is 32. And actually, in this case, so here it was vect, and here it is CMOD 2 graded vector spaces. So far for k equals 2 and k equals 3, actually nothing new. The first one where you see something new is for k equals 4. So for k equals 4, the fusion rules I've written down them here. Doesn't matter so much, I just evaluated this formula. The two corresponding fusion graphs is one of those anti-diagonal graphs, which of course is Perron-Frobenius dimension 1. And this funny thing here, which looks like this, so it's a line. So it looks like this. It has a lower diagonal, and there's an upper diagonal, and it has zeros in the middle of the corresponding size. Okay. And you can check that this has this Frobenius Perron dimension, so pi over 4 basically. And 4 was the level. So whatever, you can sum everything up and you get this Perron Frobenius dimension. In general, okay, in general, what you can do is for k equals 2, you still have this one generating object. Its fusion graph is the easiest graph you can imagine. It's a line. It's a line graph with edges going from left to right all the time. And the Perron Frobenius dimension is 2 times pi over k. Okay, so this is kind of a funny pattern. So you write down those fusion categories. From 4 onwards, they are kind of new. They are not vector group spaces or weighted vector spaces. So, and the Perron Frobenius dimensions for those guys are also very easy. They are basically given by a closed formula, right? 2 cosine pi over k is certainly a very close formula. And the corresponding fusion graphs are just these line graphs. The easiest non-trivial graph you can imagine, a line graph. Of course, they are strongly connected, right? So these things are certainly generators. Okay, so this is one of those examples of those fusion categories. Very easy one. Let me say it again. Basically, for SL2, you could choose a k, and you get simple object in the index by 0 up to k minus 1. I have a closed formula for the fusion rules, and I discuss a little bit how the graphs look like. You could now try as an exercise k equals 5 using this formula and write down the graphs. It's not so bad. It's actually quite a lot of fun. I haven't told you how to construct those categories, and as I said, I postpone this to a later lecture. You can also take a subcategory. If you look at this formula here, you will realize that you can also only take the even objects. Otherwise, it's exactly the same. But now I take only 2, 0, 2, 4, and so on. And otherwise, it's exactly the same. And I call it the fusion category associated to SO3. Even representations of SL2, if you want. So I take only the even indexes. And this one is another family of those well-indexed categories. And I can discuss a little bit the small cases. And they are for k equals 2 and for k equals 3, that's vect. For k equals 4, you get still something you have seen before, graded vector spaces. For k equals 5 comes our little category from before, namely the Fibonacci category that I discussed before. It had this funny fusion graph, remember this one? And it had the golden ratio as a PF dimension. Okay. So it wasn't that bad, it was very nice. For k equals 6, it's already something new. This is how the multiplication table looks like. For k equals 6, it has this funny generator here, which now is a line, but now with a loop at every second step. So 2, the next one will be 4. And the PF dimension of this one is 2. You can calculate it. And there's another anti-diagonal one. And the anti-diagonal ones are always PF dimension 1. For k equals 7, here's a multiplication table. This is how the graph looks like. Maybe now you see a pattern. So there's an even and odd difference, and basically, but basically what the graph of this generator should look like is it's a line. Again, you have edges in any direction, and depending on whether it's even or odd, you have an additional loop at the vertices. Never at the starting vertex, but otherwise additional loops. So this is how it looks like. It just depends on whether it's even or odd. Right? It's a line, you have loops, and depending on whether it's even odd, you have a loop at the end or not. And this is quite a huge family of those things. So for SL2, you basically have a generator, which is a line. For this even part, the SO3, you basically have a generator, which is a line with loops. And this funny proposition tells you that there's almost no redundancy. So almost all of them are non-equivalent. So you get these huge families of fusion categories. Namely, they're equivalent for different choices, if and only if k is equal to k prime. So k was one of my choices. And something with other associated choice, which I haven't discussed so much. So there's another associated choice, which is basically the quantum parameter, which I will discuss later when I have to construct those categories. But for now, just another choice. Doesn't matter so much. But basically, what this theorem wants to say is they're almost never isomorphic, and you could see this here, right? You get vector spaces, the more two vector spaces, you get something more fancy with 2 cosine pi over 4, then you get something even fancier with 2 cosine pi over 5, and so on. They're basically never isomorphic. So you get this whole family of non-trivial examples of those fusion categories. Okay. And now you wonder whether you can classify those things. So let me try to address for the rest of the lecture classification problems. And well, the answer is no, you can't. You already can't really classify finite groups. So how can you classify something that apparently wants to categorify finite groups? Well, you just can't. But you can try something. You can try to classify them by certain numerical invariants. There's the following thing. You can try to classify them by fixing what the Grothendieck ring is. So basically fixing this multiplication table here. Fix. Oh, that's one way to do it. You can fix just the number of simple modules. So you could fix this. So that's more like classifying groups with the same order, like all groups of order 12, whatever. Or you can fix the PF dimension. So you can fix, where is it? This one. So you can ask for, what are the fusion categories with per order for Venus dimension 6, for example? Right, to fix a numerical invariant, I told you 3 of them, and you can try to ask for whether you can classify those fusion categories of this corresponding numerical invariant. And of course, if you would have a classification for each numerical invariant, you would have a classification of all fusion categories. It's like breaking your problem apart into smaller bits and pieces. Okay, before we jump right into it, as I said, this is even in the lecture notes, this is a bit sketchy because it's not so easy to prove, right? But I give the references. And the arguably most important theorem in this setup is what is called Ocniana rigidity, which is a uniqueness kind of statement. And it says the following: if you have fixed your Grothendieck ring, then the number of the corresponding fusion categories is finite. So this is just really basically saying classification problems are not hopeless, because for fixed numerical invariant you would get a you get a finite answer. This is still far away from classifying those things, but at least you can expect a finite answer. And it's really a deep theorem. It's really not easy to prove. but it's telling you that classification results are possible, right? For a fixed numerical invariant like the Grothendieck group, you would get a finite number of indecomposables, the finite number of fusion categories. So classification is possible. This is just saying classification is possible. Okay, so the first thing you would try is to just fix the Grothendieck rate. And you can write down several classification results, which I'm not now going to discuss. So for example, if you would fix that, if you would ask what are the fusion categories with whose Grothendieck ring is just a group, a finite group itself, and it will turn out, well, we already know all of them. These are G-gated vector spaces up to a twist. Okay, so the classification results for things that look like group downstairs are groups upstairs. This is actually a good start. And that's not so hard to prove. All right. And I give you another. This is the first non-trivial classification result. Group-like things are group-like things. Groups are categorified by groups, basically. I give you here another example of a certain category, which is a little bit funny. It has Perron-Frobenius dimension square root of 3. And it's defined as follows. So you take a finite group, it has a name. It's not quite a category, it's just a Grothendieck group, right? We are fixing a Grothendieck group, so it has a name. Tabara-Yamagami fusion ring in this case. And it's just the following. You attach just one extra element, X, to a group ring. And X has those properties. So it eats group elements. And if you square it, you get all other group elements. And you can write down the corresponding, let's say for G equals Z mod 3, you can write down the corresponding fusion graph. And you would get, well, it's a Perron-Frobenius dimension square root of 3. And in general, what you would get is, for any finite group, you get this family of fusion rings, which have the following property: group elements of Perron-Frobenius dimension 1. X is of Perron-Frobenius dimension square root of the order of the group, and this thing is of Perron-Frobenius dimension 2 times the order of the group. So here we kind of classify things of Perron-Frobenius dimension, the order of the group. And the next easiest thing is to try to classify things which are twice the order of the group. And there is also a classification for those results. And it basically works as follows. So whenever you see something that decategorifies to those rings, then there exists a fusion category, which is the corresponding whatever. I haven't told you the construction of those things, but there exists one for any abelian G, and you can parameterize those given basically by a certain numerical datum. So in this case, with this choice of Grothendieck ring, you can classify exactly the corresponding fusion categories. Very much like here, you just get a slightly more complicated answer because you have a slightly more complicated ring downstairs. And you can go on, like fusion categories of rank 1. So now let's fix the rank. Okay, let's fix the rank. Fusion categories of rank 1 are vector spaces, basically. So if you have a fusion category, if you have a Fiat category of rank 1, then it's vector spaces. And if you have a tensor category of rank 1, and let's say the underlying characteristic is 0, then the thing is also vector spaces. So classification by rank is, by the way, we'll see it much more complicated than classification by a Grothendieck group or periodic Frobenius dimension. But at least for rank 1, you basically get vector spaces. And I actually give a proof that's not so complicated. But let's ignore it. The point where you see characteristic 0 turning up is because you will see binomial coefficients. Okay? And they're just really ill-behaved in characteristic P. Anyway, so let me draw a line here because it might be a little bit too quick. Let's go back. So what have we done? I try to explain the philosophy of classifying fusion categories. And there are 3 numerical invariants you can try: the rank, the Grothendieck group, the rank, or the periodic Frobenius dimensions. For the Grothendieck group, I showed you 2 results, classification results. If it looks like a group, it's a group upstairs. If it looks like a group downstairs, it's a group upstairs. If it looks a little bit like a group, this were those Tambara Yamagami fusion categories, fusion rings, then it also exists upstairs under the assumption of being abelian, and you can classify it by some numerical data, which is not a bad start. So everything that kind of looks like a group downstairs already looks like, or also is a group upstairs. Classification by rank is much more complicated, already for rank 1, right? So in this case, if something looks like vector spaces downstairs, it is vector spaces upstairs. In this case, if rank is 1, then you would think, oh, it can only be vector spaces. Rank is, remember, just a number of simple or indecomposable objects. If it's 1 downstairs, then it should be vector spaces, but it's already tricky, and you see binomial things turning up, and it's not so easy. So rank is a very worse, in some sense, way to numerical invariant if you want to do classifications. In particular, Ocniana rigidity, this thing that classification is possible, assumes that the Grothendieck ring is finite. So it doesn't say anything about the rank being. So for a fixed rank, there could still be infinitely many solutions. So doing something by rank is much more complicated. And as you see here, which is the next proposition I'm going to explain at least a little bit, and actually explain also the proof strategy, which I will skip here totally because just the strategy will take half a page. So it's not so easy, but basically try to write down conditions on the Grothendieck group. So this was rank 1. So let's go to rank 2, right? Next step would be rank 2. And you already see 1, 2, 3, 4, 5 cases of what could happen in rank 2. So for rank 2, fusion categories are equivalent to 2 copies of vector spaces, Z mod 2 graded vector spaces, twisted Z mod 2 graded vector spaces, or 2 versions of those Verlinde things I showed you above. Which is quite a long list for rank 2, right? Remember, finite groups of rank 2, you only have Z mod 2. Fusion categories of rank 2, you have copies of vector spaces, Z mod 2 vector spaces, twisted Z mod 2 vector spaces, and Verlinde categories. That's already complicated. I don't even want to go to to rank. Well, I stayed rank 3 here, but as you can see, it's long. Okay, I'll skip this part because I haven't discussed the proof anyway. So the next, I skipped this part. You can read it in the file. So the next case would be rank 3, and you would. So rank 3 means you have 3 simple objects, 1, 2, 3, and here's the classification. And it's long. So the only possible fusion rules are those. You have 2 possible fusion rules. But the second table actually depends on parameters. So, and from those parameters, only the following cases occur. So you have A, B, C, D, E as potential fusion rules. This is how it looks like. Don't worry too much. It's just some kind of numerics you do. I just want to give you a flavor how things will look, right? So for rank 3, this is a multiplication. You have 5 possible multiplication tables. And then okay, that's how you would start. You would basically write down the possible multiplication tables, and then you would try to find the corresponding fusion categories. For A, the only solutions you will find is, well, there should be at least one fusion category of the corresponding rank, namely Z mod 3 graded vector spaces. And yes, you will find Z mod 3 graded vector spaces for type A. For type B, you will find one of the Verlinde categories. So this is Verlinde. And this is also Verlinde, which you also find for C, plus twists. For D, you will see S3 turning up, so representations of a finite group. That's something we haven't seen before. I told you basically everything is vect G, rept G, or Verlinde, and you see it in this classification. So for A, you see, well, G-graded vector spaces. For B and C, you see Verlinde. And for type D, you see rept S3. And for type E, this is kind of an exotic case. It's a certain subfactor of type E6. Doesn't matter so much what it really is. The point is, this is how usually those classifications look like. You have group graded things, you have reps of groups, and you have Verlinde, and you might have a finite number of, or you might have a certain number of exotic examples. Proofs of these things are really, really hard, because what you need to do is you first need to write down basically those tables here, and then you need to find the categories. And finding the categories isn't all that bad, because you have something like, so those examples are, maybe I shouldn't use, right? Those examples are usually easy. S. And the exotic ones are usually hard. They're really hard to construct, And you kind of need to find some tools to even write them down. Anyway, this is just to give you a flavor of what's going on. So when you classify fusion categories, you will kind of always see the same pattern. Vect G, rep G, or finite dimensional modules of a group. So this is my blue example here. You see Verlinde categories turning up. This is my green example, and some exotic things. This is how any good classification looks like, by the way, anyway. You have nice families that you like, and then you have some exotic things, which are usually hard to understand because they're exotic, right? Exceptional things are usually hard to understand. But in some sense, it's kind of funny because they're exotic, so you shouldn't care too much. But they will turn up, so you should be aware that they will turn up. And then I kind of want to go to the next part, right? We have seen by Grothendieckering, we have seen by rank. So from rank 4 onwards, it's just very, very hard. Rank 3 was already I've seen one of those exotic things, which I'm not going to explain in the whole lecture. I at least will construct those Verlinde categories, but those exotic things are really not easy to construct. If you don't know much more about the theory, it's just not easy to construct. So the final thing would be to look at PF dimension. And for PF dimension, you surprisingly get a very nice answer. So PF dimension seems to be, in some sense, is the best way to order your categories, which is a bit surprising. In order to do so, I need some some technical lemmas or theorems. Doesn't matter so much. Let me just skip them. You can read them in the file. But basically, a much easier thing than before is if PF dimension is 1, then the are vector spaces. Okay. And this is already nice, but this is just a slice of a much bigger thing, namely uh, the analog of all groups of prime order are cyclic. Was my starting question from the first part of this lecture. The analog is really this proposition, which says if Perron-Frobenius dimension is a prime, then it's Z mod P graded vector spaces. This is really the analog, right? All finite groups of prime order are cyclic. All fusion categories of Perron-Frobenius prime order are cyclic graded vector spaces up to this. This is really a beautiful theorem. This is really cool, and it's not so hard to prove. It's not so hard. It's too hard for this part of the lecture where I'm basically trying to give you a feeling what's going on, but it's not so hard in the end. So this is pretty good. So this is pretty cool. And they actually only call it a proposition because I don't know. It could also call it a theorem. So this is a pretty cool theorem. It's a much better thing than if you would fix the rank to be a prime, as we have seen, 3 above. The classification was kind of a bit crazy, right? And here it's just much cleaner, much nicer. So PF dimension is kind of better and much better invariant than the rank. The rank is a little bit too crude. And let me finish. This is really the last thing I will do. It's really, I call it an extraordinary fact. And this is really an extremely important fact. So it basically was discovered already by Jones in the 80s. And it basically was the reason why he, in the end, ended up getting the Fields Medal. He got the Fields Medal for the Jones polynomial, but this was kind of the first instance of the Jones polynomial turning up. And you will see that in one of the later lectures, because I will basically try to construct those Verlinde categories using Jones polynomial approach, like Temperley-Lieb and Brouwer categories. And here's a classification by PF dimension. And it's amazing. It's amazing. It's pretty simple in the end. It boils down to computing certain eigenvalues of matrices. So let's say you have a fusion category. And let's say you have a simple fusion generator. And let's say the fusion generator is of PF dimension smaller than 2. Okay? We know that it's at least PF dimension 1, so let's say it's in the slice between 1 and 2. It's basically the first thing you would try, right? If you know it's bigger than 1, and then maybe the first bound you would set is 2. Sounds reasonable to me, and you get this amazing answer. Namely, the PF dimensions are always those that I've shown you above, so it's 2 cosine pi over k. This should already tell you, oh, wait, probably the associated fusion categories are the Verlinde categories that I showed you above. And yeah, this will be the answer. But for now, just the possible Perron-Frobenius dimensions between 1 and 2. Remember, they basically could be any real number, but it turns out that they are only cosine pi over k's, which is pretty amazing. There's still infinitely many, because k can be anything, but they are certainly in some sense discrete. There's a discrete set in between 1 and 2. And it gets better. The fusion graph of those things, so it's not just that you can write down the PF dimensions easily, but the fusion graphs is what we have seen before. It's this line graph. And there's a symmetry on the line graph. If you think about it a little bit, you can basically take this symmetry of the line graph, and you could fold the graph, and you would get whatever is called this graph. It's the second easiest example of a graph. it's a line, but there's one splitting at the end. It's called a type D graph. This is called a type A graph. So type A is just a line, that one we have seen before. Type D is, well, a line with a split and some exceptions. And they're usually just three of them. They're called E6, E7, and E8. Okay, so let me say again what's happening here. This is really, really amazing because it's so nice and important. So try to classify something by PF dimension, and maybe the first bound you would set is 2, right? And it turns out that for 2, there are only, well, these, so 2 families of solutions possible, a line graph or a splitting line graph, and you have 3 exceptions, which you basically can ignore anyway. They only turn up to a certain point, and then this is not an infinite family. So they have 2 infinite families you should care about, and some exceptions, and this is called the ADE classification type. And it's one of those amazing things, theorems where you see an ADE classification. ADE classification, if you haven't seen them before, it might look a little bit random, but they will turn up everywhere in mathematics for some really strange numerical coincidences. Here's one. And because it's so important, I say it again. Fix the Frobenius Tappone dimension to be at most 2, strictly at most 2, and you will see exactly those fusion graphs turning up for the generator. Amazing, amazing statement. Not just their, this is a classification, but the classification is then for all of them, there exists actually a fusion category. So this is kind of like a statement like the worst thing, the only thing you can imagine is that those guys turn up, but there also exists one, and it's usually just of the form. So in type A, it's exactly, so this one is exactly Verlinde, the one that I showed you above, Verlinde for SL2. And that's just an amazing statement. Right? For Perron-Frobenius dimension small, you get Verlinde categories for SL2. And so those are a bit funny, as I said. And this is basically also a Verlinde. It's not quite a Verlinde, but it's a symmetry among the Verlinde. Let me just call it a Verlinde. So for small Perron-Frobenius dimensions, you get Verlinde categories. So what have we seen so far? So for Perron-Frobenius dimensions being primes, you get group things. For small Frobenius Perron dimensions, you get Verlinde categories. That's a pretty nice classification-like thing. And up to this example that I did in rank 3, up here, the only thing we ever saw are group-rated things, representations of groups or Verlinde things. And this is kind of a pseudo statement. So a pseudo theorem that people usually use in, obviously this is a theorem because I don't tell you what 4 is, but kind of a pseudo theorem you should keep in mind is all fusion categories come in the following types: vect G, modules of G, or Verlinde. And that's basically it, up to exceptions. Up to exceptions. Theorem, the main theorem of this lecture. All fusion, we've just classified all fusion categories. They are vect G, modules of G, G is a finite group, or Verlinde categories, up to exceptions. And of course, this is a completely legit classification because I haven't told you what exceptions are, right? So, and a lot of effort is spent on studying those exceptions. So these are these exotic things. They're not so easy to construct. And the point that I will make in the next 2 lectures is exactly this one. The Verlinde categories, the fusion categories of type 3 in this case, they are the main source of quantum invariance. So I need to construct them in particular, and you will see why they are the main source of quantum invariance in the next lecture. Okay, so here are a few further exercises, and then we'll wrap up. So I would really encourage you to do this fusion graph of S mod 5, S5. It's very, very easy and nice, and you get per Venus dimension. Just try to calculate them. And yeah, this is basically what I wanted to talk about. There are some other examples and exercise. Again, they're just try to calculate as much with those fusion graphs as possible because it's extremely explicit. It's nice and basically very powerful. The only thing you need to do is calculate some eigenvalues and write down matrices. Okay, so what have you seen in this lecture? So let me just wrap up. So basically, what we have seen is we have seen a classification theorem for those semi-simple fusion categories, which you would like to see as kind of the target of um, of our quantum invariants, and they basically come in three flavors. There are groups, uh, group graded vector spaces. They are representations of groups. These are a little bit boring. They have usually a little bit of a boring braiding. So they give you quantum invariants, but they are a bit boring, not interesting quantum invariants. And there's a third family, which I'm going to construct in lecture 9 and 10, which are the Valinde categories. And they are usually extremely good. Quantum invariants are very powerful. Um, and they are, they can be constructed diagrammatically, so it's very explicit. Um, and this is basically the story up to the exotic examples, which I won't discuss anymore in this lecture. Anyway, I hope you're next time up for a bit more graphical calculus. Today was basically very well linear algebra based, like writing down graphs and matrices. So next time we'll see more graphical calculus again by trying to construct those valid categories. Anyway, I hope this was reasonably helpful, and I hope to see you next time.